Hey there, I'm Jake, and today I'm going to introduce you a little bit to infinite sums of real numbers. Now, what is an infinite sum? Well, basically, in an infinite sum, you're just adding real numbers indefinitely. But wait a second. If I add something forever, doesn't that result into infinity? Well, not always. That is the case if you do like 1 plus 2 plus 3 plus 4 forever. Yeah, that obviously goes to plus infinity. But there are many cases where it doesn't. Let me show you one. We start off by drawing an equilateral triangle. More or less. Actually, it's terrible. Now anyway, of this equilateral triangle, we put a point on each of the midpoints of each side, and we connect them. A triangle inside a triangle. Now, this whole triangle, the area is 1 of the whole thing. This one, this triangle here that I am filling out, will have the area of what? 1/4. Now, we do the same thing on the triangle on top. And what do we get? Well, we get a fourth of a fourth. So we get 1 to the 4 to the second.
1 over 4 to the second, excuse me. Do the same thing again. Here, so we get 4 to the third.
And so on, so on. Now, what is this whole thing equal to? Well, let's analyze the triangle this way. We divide it in many trapezoids, you see, here. Now, of this trapezoid here, the colored area is 1/3. So if we consider everything, all the parts, we realize that the colored part of the whole thing will be 1/3 of the unity. Therefore, this whole sum converges to 1/3.
Therefore, we can summarize this whole result by writing the following expression. Now, we use, for infinite sums, we use a big sigma, capital sigma, which is a Greek letter that is kind of equivalent to our modern day S for sum, it's not too far-fetched, of 1/4.
Because you see it's 1/4 here over k. Because you see what always changes is the power. It always increases. With what? K that starts from 1.
Because we start from 1/4.
To what? K that reaches plus infinity. From this proof, we can see a characteristics of these kind of sums that converge to a finite number. We see that each of the following numbers is always smaller than the one before it. So like that, it converges to a finite number. But is that always the case? I'll show you now another example. Now, we want to prove
that the infinite sum
of 1 over the root of k, with k that starts from 1 and goes to plus infinity, is equal to infinity. Well, we see that this is an infinite sum where each of the numbers becomes smaller because it'll be 1 over 1, 1 over the root of 2, 1 over the root of 3, so it keeps going smaller. But it diverges to plus infinite. Well, let's see how that is so.
First of all, we start by drawing a right triangle.
And the hypotenuse will be root of k, and this catetus here will be 1. So what is this catetus? Well, this catetus will be what? Pythagoras?
Root of k minus 1, because this is the square root of this squared minus this squared. K minus 1. Now,
we draw here the altitude of the triangle, and we call this x. Now we want to find the value of x. How do we do so? Well, we apply the first theorem of Euclid, where the hypotenuse, root of k, over the catetus is equal to the catetus over its projection. Now, what do we see here? Well, we see that x will be equal to 1 over root of k. Now you see that this is the same 1 over root of k that we have here. Let's keep that in mind. Now let's imagine that we have a big protractor, a big compass, excuse me. We take our giant compass and we point it with opening it at the value of root of k minus 1, and we send it out like this. Close enough. And we see that 1 over root of k is greater than what? Than the hypotenuse minus root of k minus 1. Because by doing so with the
compass, we're basically graphically doing the subtraction. Now at this point, we got an interesting result. Let me clear out my whiteboard.
So let's imagine now to apply these as finite sums.
So we do 1 over 1, which is 1 actually, because 1 over root of 1 is 1, plus 1 over root of 2, plus 1 over root of 3, plus 1 over root of 4, plus so on, to 1 over root of k.
Now this whole thing is greater than what? Then let's do the same thing for this part over here. 1 will be root of 1 minus root of 1 minus 1, which is 0, plus root of 2 minus root of 1, which is actually 1, plus
root of 3, now root of minus the root of 3 minus 1, which is root of 0, root of 2, excuse me. Plus root of 4 minus the root of 3, plus, excuse me if I go down here, but now, so on, till the root of k minus the root of k minus 1.
Now, what do we see here? Well, we have this minus 1 that gets simplified with this 1 over here. We have this minus root of 2 that nullifies itself with the root of 3. We have the root of 3 that nullifies itself with the other one, so forth, and we realize that it always simplifies the value, which is equal to k minus 1. Therefore, what do we have? We end up with having
1 plus 1 over 2, plus 1 over 3, plus 1 over 4, 1 over square root of 3, 2, 1 over square root of 3, 1 over square root of 2, 4, plus so on, plus root of k, square root of k, greater than what? Than the root of k.
Which is the only number that we're left with. Now, taking the limit with k that goes to plus infinity of 1 plus 1 over square root of 2 plus 1 over square root of 3 plus 1 over square root of 4 plus so on up to square root 1 over square root of k is greater or equal to the limit with k that goes to plus infinity of root of k. Now, what do we see here? Well, we know how to calculate the limit of the root of k, of square root of k. Well, if we see graphically, the root of k is something like this. So, the greater we go on the x-axis, if we go with the axis towards infinity, the graph of root of k will grow as well to infinity. Not as fast as, let's say, y equals k, which would be something like this, but it still goes to plus infinity. Therefore, we can say that this thing is greater or equal to plus infinity. And since nothing is greater than plus infinity, we can say that this sum diverges to plus infinity. Therefore, we've proven this expression here. The difference between this expression and this one that we've observed before is that, well, yeah, each of the elements do become smaller as we go ahead in the sequence. In fact, we have 1, then we have 1 over square root of 2, 1 over square root of 3, and so on. But they don't get smaller at a fast enough rate. In fact, here it's the root of a square, it's the reciprocal of a root, while this is a reciprocal of a power. Therefore, this one becomes smaller at a much faster rate. Now, I hope you've enjoyed this little lesson in infinite sums. See you next time.